The fresh 3I Atlas photos subtly altered the discussion once again. What you're looking at is a single 172-second exposure from the Hubble Space Telescope, taken on December 27th. There is no enhancement applied here. No contrast stretching designed to pull out features. No structure filters. This is the object exactly as Hubble recorded it. The first thing that stands out is how compact 3I Atlas remains. The central brightness is tight and well-defined, surrounded by a smooth, relatively symmetric dust envelope. There's no sign of fragmentation, no secondary cores, no diffuse clouds suggesting breakup or shedding of large chunks. At this stage in an outbound trajectory, especially after perihelion, many active bodies begin to look messier. They smear, they puff up. Their cores lose definition as activity becomes disorganized. Stay with me until the very end if you want to see what happens next. Additionally, if you're already interested in this, you may like, subscribe, or enable notifications at any moment. Go full screen for the greatest experience, and let's go over the recent changes. This one doesn't. That matters because it tells us something important right away. Whatever is driving the activity is not coming from a collapsing or disintegrating structure. It's coming from a coherent source near the nucleus. The object is holding itself together, even while remaining active. By itself, this raw frame doesn't scream jets. You wouldn't point at it and say, "There they are." But that's exactly why it's useful. It establishes the baseline. It tells us what the object looks like without interpretation. And once you have that baseline, what happens next becomes impossible to ignore. Now let's take this exact same dataset and extract the motion. Using a Larson Sekanina rotational filter, the background symmetry is removed, allowing directional structures tied to the nucleus to stand out. This doesn't invent features. It amplifies differences that are already present by subtracting the average brightness distribution and revealing deviations from symmetry. And when we do that, the structure becomes unmistakable. Two distinct jets emerge directly from the nucleus. They are narrow. They are directional. And most importantly, they are persistent. Look first at the December 12th panel. The dominant feature is the anti-tail jet, pointing sunward toward the lower left. It's clearly the strongest emission source at that time. A second jet is present, but it's noticeably weaker, almost secondary in character. Now compare that to December 27th. The geometry is the same. The orientation hasn't changed. The jets are emerging from the same regions on the nucleus, but the brightness balance has shifted. The secondary jet has strengthened. The dominant jet has changed intensity. That shift is subtle, but it's critical. If this were simple dust shedding, you would expect the pattern to blur. Random outgassing would smear the structure. Radiation pressure would wash it out. Instead, what we see is something far more controlled. The structure stays locked in place while the relative strength of the jets evolves. That behavior tells us two things. First, the activity is organized. These jets aren't flickering on and off randomly. They're tied to stable source regions on the nucleus. Second, the variability is either rotational or intrinsic. Either the nucleus is rotating in such a way that different vents come into better alignment with our line of sight over time, or the vents themselves are changing output while remaining spatially fixed. In both cases, the underlying structure remains coherent. This is not chaos. It's modulation. And that's the key result from this Hubble update. 3I Atlas is not just active. It's showing structured, rotating activity on interstellar scales. That's not something we can casually dismiss, because it tells us this object has internal complexity, thermal gradients, and mechanical integrity that allow it to respond to solar heating in an organized way, even after spending millions or billions of years drifting through interstellar space. Which brings us to the bigger question this raises. If objects like this can maintain coherent structure, controlled venting, and long-term stability while crossing star systems, what does that say about space itself as an environment? Not as a destination we briefly visit, but as terrain that can host long-duration processes, interactions, and possibly infrastructure. And while we're watching this object unfold, there's another signal worth paying attention to. NASA Administrator Jared Isaacman recently stated something very plainly. The United States is going to build a moon base, not as a study, not as a conceptual roadmap, as an objective. In follow-up remarks, the priorities were laid out clearly. Returning to the moon, establishing an enduring presence, treating space as strategic high ground, scientifically, economically, and nationally. What this moment really represents is alignment. Better instruments, more data, clear policy direction, and a shift away from short-term exploration toward permanence beyond Earth. We are getting better at seeing what's out there, and at the same time we're committing to staying out there. So the question now isn't whether space activity accelerates. It's which comes first. Do better instruments give us better answers before we build permanent footholds? Or do those footholds expose us to questions we aren't ready to answer yet? Because as 3i Atlas is quietly demonstrating, space isn't empty. It's structured, it's dynamic, and it may be far more organized than we once assumed. Drop your thoughts in the comments, and if you want the next update as soon as new data arrives, make sure you're subscribed.